Hello, everyone. Today we are going to start our fifth lecture of gravitation. Uh, you have completed Newton's law of gravitation, and the gravitational potential was discussed in the previous class. So, I hope you have gone through all those lectures. So, in today's class, we are going to discuss about few more things like the escape velocity, and the main thing is going to be the satellite and planetary motion. This is the main highlight of this lecture. So I hope you all are here. So let's start the session. Okay. So first of all, we will start with the escape velocity. You have heard the term escape velocity. What is the meaning of escape? Escape is the word that you can say to leave something. What if I say, what is the exact meaning of escape velocity? Suppose there is you are standing on a earth and you are throwing some object in the vertically upward direction. What will happen? Good evening, Bacha. Good evening, JNV Mahe. So if I throw some ball in the vertical upward direction, it will come back to us. If I increase the velocity, increase the initial velocity, it will go further high, further higher, higher. And a situation came when it doesn't come. So the minimum initial velocity given to a body so that it just escapes the gravitational field of the earth is called escape velocity. So I have written it for you. What it says, the minimum velocity required, or you can say minimum initial velocity required for an object at Earth's surface so that it just escapes the Earth gravitational field. This is what escape velocity. How we denote it? We denote it because it is an initial velocity, so it is denoted by U, and it is escape velocity, so it is denoted by UE. This is the symbol of escape velocity. I think the thing is clear to you. What is the meaning of escape velocity? Now, we can derive a relation for the escape velocity. It would be like, consider this system here. Consider this is the Earth, which has a mass me and has a radius re. This is our Earth. And a small mass, small m, is at the surface of the Earth. This is the whole situation. Now, what I am trying to do, I will throw this ball in the upward direction. And what is the meaning of minimum velocity? When I throw this ball in the upward direction, certainly its velocity will decrease while moving in the upward direction. So, what I say that after crossing the gravitational field, or you can say after reaching infinite distance, or after crossing the gravitational field of the Earth, its velocity is just zero. It just escapes the gravitational field without any velocity. So when it reaches the infinite height, like this is our Earth, and I have thrown the ball like this, and it reaches the infinite height or crosses the gravitational field, or you can say it reaches the infinite height, but its velocity is zero. Then the initial velocity given, then the initial velocity given is known as escape velocity. I am repeating my words. I have a ball. I have thrown it in the upward direction. The velocity that I gave to the ball initially will be called as escape velocity if after escaping, after leaving the gravitational field, it has no velocity. Clear? So this is the situation. The mass of the Earth is me. Radius of the Earth is re. So we can apply conservation of energy here. This is our initial situation. This is our final situation. And we can apply conservation of mechanical energy. What it says, kinetic energy initial plus potential energy initial is equals to kinetic energy final plus potential energy final. This is what? Conservation of mechanical energy. This is complete mechanical energy initial, mechanical energy final. I hope it is clear. Now, just put the values. Kinetic energy initial, if I talk about, the ball has initial velocity ue. So if you write kinetic energy initial, it will be half mass of the particle is m and its velocity is ue square. This is kinetic energy. And if I write about potential energy, you have learned about the potential energy, I hope, in the previous lecture, or I think lecture third, that potential energy is what? Minus g m1 m2 upon r. That was the gravitational potential energy you have learned. So I will write it directly that potential energy is minus g, mass of the earth is me, into mass of the particle is m, divided by the separation. Separation is re. This is what u initial. Now what I say, that after reaching infinite distance, its velocity is zero. Velocity is zero, that means kinetic energy is also zero. And after reaching infinite distance, its potential energy will also be zero. You can place the value of separation. Separation will be infinite, then potential energy will be zero. So what it becomes, if I transfer half m ue square is equals to g mem divided by re. I think it is clear up to this point. Now, if I cancel things out, you can see this m will get cancelled out. So ue will be, if I transfer something, 2 will be transferred here, 2 g me divided by re. This is our escape velocity for Earth. Escape velocity for Earth. Me represents mass of the Earth, re represents radius of the Earth. The same thing can be utilized, the same formula can be utilized for any planet. If I say that what will be the escape velocity from the moon, what will be the escape velocity from the Jupiter, then you need to replace these masses and radius with that planet only. All things will be sorted. So this is the escape velocity. And I think you know all these values. Capital G, you know, mass of the earth is also known, radius of the earth is also known. If I put all these values, then it came out to be U is equals to, any one of you remember, I think that is 11.2 approximately kilometer per second. This is what the value of escape velocity. I hope it is clear to you. If you have any doubt, you can ask me. Now, we can replace this formula into another form. I hope you know the relation between capital G and small g. So we can replace this formula for in terms of small g. What can I do? We have derived UE is equals to 2g me divided by re. That will be in under root, na, actually. Because under root is what? UE square. This is square will come to the under root. Now, this is the actual relation. Now, what if I say JNV PKD2? Okay. You know the relation, I think someone of you might have remembered the relation. G is equals to GME divided by RE square. I think this relation is remembered by you, I hope. This should be discussed in the, I think, first or second lecture of the gravitation. So someone of you are joining late in the session, no issue. So this is the only thing that we have discussed till now, escape velocity. Now I say, can we convert this relation into the form of small g? Yes, we can. What we can do, if I multiply this term with the RE and divide it by RE with the same term, can you see that GME divided by RE square? It will be small g. This GME by RE square is small g. So we can write here UE will be under root 2 is here. This term is small g and this is radius of the earth. This is another form of escape velocity. You can remember either of the formula and it will work for you. I think concept of escape velocity is pretty much clear. The minimum initial velocity required so that the body escapes from the gravitational field. I think it is clear. Now moving further. What are the punchlines? If you see the formula written here of the escape velocity, can you see that? Can you notice that this escape velocity is independent of the mass of the body thrown? The mass of the body which is thrown was small m. The mass of the body which is thrown was small m. But in the relation, in the expression for the escape velocity, that small m is missing. You can see both the relations. Then we can conclude that it is independent of the mass of the body which is thrown. This is the main punchline here. Escape velocity depends on the mass of the planet and the radius of the planet. You can see the relation. The escape velocity depends on the mass and the size of the planet. And the second thing, this is the most important thing, position from where the particle is projected. Whether you have projected the particle from the surface of the earth, in driving the relation, we have thrown the particle from the surface of the earth. But in some situation, in some questions, there is a possibility that particle is thrown from some other point. So the main thing is escape velocity depends from the point of projection. You need to keep these punchlines in your mind that escape velocity depends on the position from where the particle is. For example, if I say this is the earth and particle is thrown from the surface of the earth, then escape velocity will be different. And if I throw the particle from this point, then escape velocity will be different. So escape velocity depends on the point of projection. And on what factors it does not depend. The next heading is escape velocity does not depend on. Again, I have told you mass of the body which is projected. It does not depend on the mass of the body which is projected. The mass, this mass is independent. And the angle of projection. Angle of projection is what? Whether I have thrown it at an angle 30 degrees, 60 degrees, whatever may be the angle, but the escape velocity will remain the same. It does not depend on the angle of projection. So these punchlines need to be remembered by you while dealing with escape velocity. So on the next slide, there will be few questions for you as a concept test. Try to do them. Okay. The first question on your screen, you can take 1 minute of time in solving the question. I think everyone should at least give it a try. Okay, do it. I'm waiting for 1 minute only. Give it a try. Just do it. Anyone who has attempted? Okay, let's see. Okay, in the previous slide or in the previous discussion, what we have discussed, suppose this is the Earth. And a particle is thrown, this ball or what is the given, something object is thrown like this. And it is thrown with an velocity which is n times the escape velocity. So escape velocity is ue. And the velocity is given to this object is n times of escape velocity. So can you see the initial velocity is n times of ue? So what are they saying? What are they asking in the question? What will be the residual velocity at infinity? The situation may look like this. After throwing the ball, suppose Earth is here. This is the same position of the Earth. And the ball reaches the infinity. And at this point of time, its velocity is v. We need to calculate this velocity v. This is our question. Again, mass of the Earth, I am taking as m, radius of Earth taking as r. So you can say me, re, whatever you want, you can choose. This is the situation. Now, from conservation of energy, what we can write that initial kinetic energy plus initial potential energy is equals to final kinetic energy plus final potential energy. I think this concept is pretty much clear. Conservation of mechanical. That's why I'm saying that don't always remember the formula. In some situations or in most of the questions in JEE, this situation will be from basic. You need to use basic fundamental relation. And the fundamental relation was conservation of mechanical energy, or you can say mechanical energy. So this is our initial situation. This is our final situation. Now apply conservation of mechanical energy. Kinetic energy initial will be, you will say K initial will be half mv square. Is it clear? That will be half mass of the object I am taking as m, v square. Initial velocity is what? This is our initial velocity now. So square, if you square it, it will become n square ue square. Just respond me in the chat box whether it's clear to you or not. Are you listening these things or not? This is the initial kinetic energy. Now, if I write about initial potential energy, then it will be negative of G. I think you have remembered the relation, na? G m1 m2 upon R. So G, one mass is me, Earth. Second mass is small m, divided by the separation between them is what? Radius of the Earth. And radius of the Earth is what? Re is equals to. Now, I have given more than the escape velocity to the particle. Then after crossing the gravitational field, it will not have zero velocity because I have given some extra velocity to it. So its kinetic energy will not be zero. I have assumed its velocity to be v. So kinetic energy will be half m v square. Plus u final is what? Zero. Why u final is zero and k final is not zero? U final is zero because the particle is at infinite distance from the Earth. If it is at infinite distance, then gravitational potential energy will be zero. Now you can just need to simplify. What can I see here? That we can cancel small m, small m, small m, and small m. It can be cancelled out. What's remaining? The remaining thing is n square. What is ue? You have learned UE as 2GME by RE in the previous slide. I think you have learned now that UE is what? Root 2GME divided by RE. This is what UE. If you square it, it will become 2GME divided by RE. Square root will gone. And this 2 is here. Minus GME by RE is equals to half V square. I think it is clear. This 2 will cancel out. You can take GME by RE as common. GME by RE as common. Remaining term is n square minus 1 is equals to half V square. Again, by simplifying it, 2 will be transferred here. So it will become 2 GME by RE n square minus 1 is equals to V square. Can you identify what is this 2 GME by RE? What is this 2 GME by RE? 2 GME by RE is what? Escape velocity square. So this is UE square n square minus 1 is equals to V square. So V is UE under root n square minus 1. This is the final result. If you want to ask, you can ask any of the step in these in the question. Otherwise, I will move further. This is pure calculation. Physics is up to the first step, or you can say up to the second step. Physics is there. After that, this is just pure calculation. Nothing concerned with the physics. If you want to ask, you can ask anything. Otherwise, I'm moving further. There is one more question for you. After that, we will move towards satellite and planetary motion. Okay. Take 1 minute of time in solving the question. Question is on your screen. And nobody is participating in solving the question. That's not very cool. The question says a particle is projected vertically upward from the surface of the Earth, which has a radius RE, with a speed equal to 1/4 of the escape velocity. In the previous question, the velocity was given as n times. Now the velocity is 1/4. What is the maximum height attained by it from the surface of the Earth? Give it a try for 1 minute, and after that, we will solve it. The time starts. I think there must be or there might be a leave of Pongal na, in some of the schools or some of the students, I think. Let me know whether it's the case or not. Okay. So should I start now? This is the same kind of question actually. There's nothing wrong in it that you can't do actually. Again, there is a surface of the earth. There is a earth, and a particle is projected in the vertically upward direction with a velocity one-fourth of the escape velocity. So what is the escape velocity? You will say UE is the escape velocity, and it is thrown with one-fourth of the escape velocity. So this is the initial velocity given to the ball. Radius of the earth is RE, mass of the earth is NE, that we can take. Okay. What is the maximum height attained by it from the surface of the earth? Let's suppose this is the situation. Again, this is the earth, and ball reaches up to this height. First of all, tell me whether it will escape from the earth or not. Can it escape from the earth or not? Or it will return back? Can anyone answer? Can anyone answer? Okay. So now, again, we are going to use conservation of mechanical energy. What it says, this is quite a few times that we have used Ki plus Ui is equals to Kf plus Uf. Someone of you might be wondering that this is the uh, concept of work energy and power that we are using it in the gravitational chapter. This is the most important concept, or you will use this concept in the 12th as well. In most of the situations, you will use this concept. So this is a very good concept of conservation of mechanical energy and quite useful as well. So what if I say, if I write kinetic energy initial, this is our initial situation, this is our final situation. You need to identify these situations. The ball reaches a maximum height of h. If it reaches a maximum height of h, then can you say that at this point, its velocity will be what? If h is the maximum height of the ball, then at this point, what will be its velocity? You will say its velocity will be zero, sir. Because this is the maximum height, it cannot go away from that. It cannot go beyond this point. That means at this point, velocity is zero. It will return back. So if I write kinetic energy initial, this is the initial kinetic energy, that will be half. Mass of the particle is m. I am taking it as m. It's not mentioned anywhere, and you know that it will be cancelled out. So I am taking it as m. And initial velocity square. Velocity is ue by 4. If you square it, it will become ue square divided by 16. I think it is clear. This is what kinetic energy initial. Now, if I write potential energy initial, it will be become minus g me m divided by re, because particle is at the surface of the earth. Now, final kinetic energy, if I write this is the final situation, final kinetic energy of the particle is 0, minus final potential energy is what? G MEM divided by separation is what? From the center, the separation is RE plus H. Can you see this separation? RE is what? This is RE, and this distance is what? H. So RE plus H is the total separation. Now again, you need to solve it out and you will get the answer. Can I leave it to you? Can you solve it? You can solve it like that. M will be cancelled out in the whole equation. You can place the value of UE from the escape velocity relation, and after that you can minimize the value and you can solve for H. I hope this can be done by you, and I hope you will get the answer as RE by 15. I am not solving the question ahead. I have placed the values. You need to solve it and you will get the answer as RE by 15. This is what H will be. After solving, H will be RE by 15, because I need to discuss some more concepts here, some more new concepts here. That's why I'm not solving it out. You can solve it out easily. It's a quite simple mathematics. Moving further, if you have any doubt, you can ask. Satellite motion. Now, again, this is the important thing. You all have heard about satellites. Some are natural satellites and some are artificial satellites. Our Earth is a planet which revolves around a star, and Moon revolves around the sun. So, Moon is a satellite. So, what is a satellite? Satellite is a mass or a mass body which revolves around a satellite, which revolves around a planet, is called a satellite. I'm repeating my words. What is satellite? A body or a mass which revolves around a planet is called a satellite. There are two types of satellites. One is natural, other is artificial. Earth has a natural satellite, that you know, that Moon, and we have lot of artificial satellites. Our ISRO is doing a very great job in this term, in this aspect. Actually, they are transmitting a lot of satellites every time here and there. So what actually we are going to deal with the artificial satellites? What we are going to deal with the artificial satellites? Suppose what actually happens. I'm just giving you an overview of the satellite. Suppose this is our Earth, and when we launch an artificial satellite, it will go. I'm not drawing a perfect diagram. I'm just drawing a simulation kind of thing. Everyone of you have seen the launching of these satellites. A rocket launches, it just goes vertically upward direction, like that, like that. It just goes vertically upward direction. And after reaching a certain height or certain distance, it just breaks up, and few rocket launches from it here and there, and a artificial satellite, or you can say a satellite, just launches, and it revolves, starts revolving in a orbit. This is what satellite is. First step is the it is launched in the vertically upward direction. After reaching desired distance, some stage two occurs, and in stage two, some of the rockets were launched in the opposite direction in which it is to be revolved. If it is to be revolved in this anti-clockwise direction, then in opposite direction, some rockets are launched from the satellite itself. And due to this, it starts revolving in this direction and achieves a certain velocity. And this velocity is decided by the scientist before transmission. So what we are going to discuss here, what should be the velocity? What should be the speed of the satellite in a particular orbit? That's our main concept. That's our main idea that we need to discuss here. Listen to me again. What are the things that we are going to discuss? If suppose in future you become a scientist and you want to launch a satellite and you want to establish it in a orbit. If a satellite is established in a orbit, it continues to revolve in that orbit with the same velocity. Then how will you decide that with what velocity it should revolve in a particular orbit? That's what our task is. So let's start with our task. Speed of the satellite in a particular orbit. Just suppose, again, I'm drawing the diagram. Suppose this is a planet. I think it's not that much circular, but you can relate. If I delete it, you can relate, because this is our Earth. Let's suppose it has a mass m and radius r. I'm not driving it especially for Earth. You can use it for any of the planet. This is the center of the planet. Now a satellite is launched and it is revolving. This is our satellite. which has a mass small m. It is revolving in a circular orbit like this. This is a circular orbit. I'm writing it here, orbit of satellite. And this orbit of satellite is I'm taking as small r. And what I can say, let's suppose the height of the satellite from the Earth or from the planet's surface is h. And this height, this distance is what? R. So can you see that small r is equals to r plus h? This is quite visible. So I need to calculate the speed of the satellite. Let's suppose the speed of the satellite is v. When the satellite revolves in a circular orbit, it there must be a centripetal force. And this centripetal force is applied by the gravitational force. So what I can say, the centripetal force, that is m v square by r. R is what? This r is what? The radius of the orbit of the satellite. Centripetal force is provided by the gravitational force, the attraction force of the planet and the satellite. So gravitational force is what? G m divided by r square. This yellow one is what? This is a planet. It might be Earth, might be any other planet. Most of the times when we deal with artificial satellites, it's Earth only. So again, can you see that if I want to calculate the speed, this mass m will be cancelled, r will be cancelled with the square. So speed of the satellite will be under root gm divided by r. And this speed of the satellite, if you know the mass of the planet and you know the radius of the orbit, then you can easily calculate the speed of the satellite. You can easily calculate the speed of the satellite. I think the speed of the satellite is quite clear to you. If in some cases you can place the height of the satellite is asked, or the height from the surface is given, that means h is given, then you can replace the formula as v is equals to under root gm, and this small r can be replaced by what? H plus r. You can use any one of the formula. If radius of orbit is given, then there is no need to place h. If height from the surface is given, then you can use second relation. Both these relation signifies the orbital speed. This speed is what? This speed is called as orbital speed. Speed of the satellite. I think it is clear. Next topic is time period of the satellite. I think time is already 4:30. It's over. So we are not going to discuss it here. Let's end the session. In the next class, we will discuss again.